All right, welcome back. We are on 2.7a, which is rational inequalities. There are two review questions. I would like you to pause the video and work them out. Should only take you a couple of minutes, and then I'll come back and we'll talk about them. All right, so it says, the first one says, find any asymptotes for this. This is a rational expression. Asymptote-wise, we're going to have a vertical or a horizontal. We may have neither, just depends on what we're looking at. This particular one, this is a case 2 when we talked about cases. The degree in the numerator is the same as the degree in the denominator. They both have a largest value of x squared. So for a vertical asymptote, it's always the same thing here. You're going to factor the bottom, and then it can't be anything else. At the top, I can't factor that. We could, we won't get real solutions, so we're not worried about that. Vertical asymptote then, x cannot equal 0 or -6. Horizontal asymptote, in case 2, you're going to take the lead coefficient and divide by the lead coefficient. So y cannot equal 2 over 1 or just 2. So those would be your vertical and horizontal asymptote. For the second one, it says to solve. So we are going to solve the second one. We're going to find factors of -54 that add up to -3. That looks like, let me think, that would be 9 and 6, with 9 being negative. So that means we have x minus 9, x plus 6, greater than or equal to 0. So x in this case would be a 9 and a -6. If we drew our number line, we would have -6 over here and 9 over here. This thing is a quadratic pointing upwards, so it's doing something like this. They want us to have greater than or equal to, so greater than just means above the line. This would be true, this would be true, this would be false. We can check real quick. If I put in 0, it says -54 is going to be greater than or equal to 0. That's not true. So we got two pieces to this thing. The two pieces will end up being the following. We know that it's going to be everything from -infinity all the way up to -6, and we are including that because there's an equal sign. In union with, square bracket again, we're including 9 all the way up to +infinity. This would be the solution to that one. All right, a rational inequality is any inequality that can be put into that same form we've been talking about, where f of x, or where f is a rational function. Always put the rational inequality into one of these forms to solve. So this one is already in that form. There's nothing unusual here. So we are going to be doing the following. We have to solve this thing. Now, there are going to be two situations, basically, that we got to talk about. Vertical asymptotes are always going to be x can't be a certain number. That is going to be a boundary of some sort. And then the top part, we're going to solve that for 0. So we're basically going to take the numerator, set it equal to 0, and solve this. That's going to be 3x is equal to -3, so x is equal to -1. And then bottom, we're going to set that equal to 0. We're going to solve that one. 2x is -2, so x is equal to -1. Sorry. This is 4. That's what's throwing me. That makes this x equals -2. All right. So we've got 2 points here where this is going to be an issue. We have basically this and we have this. And one of them being this one, this is going to be the vertical asymptote. Under no circumstances can this equal, can this be equal in terms of our problem here. It will never be -2. So it's always going to have something like this. Now this is basically just what we were doing up above, basically. It's 3/2, so we're really looking at something that looks like this. It's a case 2 function. And then we can plot a point, but I already see there's a point right here, so this is telling me it's going to come up, do something like this, and we're going to have the same situation over on this side. Here's what our picture is going to basically look like. And now it says greater than. So it needs to be everything that's going to be greater than 0. Well, everything that's greater than 0 here means negative infinity all the way until we get to that vertical asymptote line. So negative infinity until we get to -2. And we are not including that as part of our answer. And that's going to be in union with everything from -1, but we are including, nope, sorry, we are not including this. There's no equal sign, so everything from -1 to positive infinity. It's just going to keep going to the right, and it's going to always stay above 0. So it's going to go all the way there. This would be the solution. This is where all of our answers are going to be found. It is the intervals in which we'd find all of those. Hopefully everybody sees how that works. In terms of doing these problems, it's very similar to that. Procedures. Express them as 0 on one side. Set the numerator and denominator equal to 0 to separate the graph into intervals. Plot the intervals. Choose a test value for each interval created by boundary points. Evaluate the function f of x at each of the boundary points to determine if it's positive or negative. Write the solution. So, same idea as what we did. Now, this one's a little bit different because now it's got a 2 on the other side. It's not 0. So, first thing we would have to do is bring the 2 over. And I'm going to leave some room here because in order to combine these two things, we are going to have to multiply this by x plus 3, x plus 3. Because we have to be able to combine those two things so that we can make one fraction out of this, which is what we had before. X plus 1 over x plus 3 minus, this is going to be 2x plus 6 over x plus 3. Then we're going to combine the fractions. Now, I'm going to change this one to a plus, make this negative, make this negative, because you got to distribute the negative through so you can combine the numerators. So we are going to have something that's going to say the following. It's going to say negative x is going to say minus 5 over x plus 3. And all of that has to be greater than or equal to 0. And now we're going to do exactly what we did before in the problem just above. We're going to set each piece equal to 0 and solve. This is negative x equals 5, so x would be equal to negative 5. And then the second one, this is x plus 3 is equal to 0, so x is equal to negative 3. This one is also our vertical asymptote. Now, we can do this one of two ways. We can create a graph, or we could still use a number line. It's really not any different here. Here's negative 5. Here's negative 3, and 0 would be over here. Now, the only difference is this is a rational function, and I'm not trying to graph this rational function. I'm actually just trying to see. But, I mean, you could look at it that way. We are basically kind of graphing this thing. Negative 3 is my vertical asymptote, so I know under no circumstances can it equal that. So what it's trying to kind of tell us here, we're trying to figure out what's going on with this thing. And we do need to check points at this particular juncture. Okay, we're going to need to check some points. So looking at this one, we just got to pick values on each side of both of these boundary points. So I'm going to start with 0. Just going to plug 0 into the equation here. If I plug 0 into this original equation, it's going to say 1/3 is greater than or equal to 2. Well, that's false. So this area over here is false. Pick a number in between here, so negative 4. If I put in negative 4 in the top, I'm going to get negative 3. Negative 4 in the bottom is negative 1, so this is saying 3 is greater than or equal to 2. That is true. So that part is true. And then negative 6. If I take negative 6 and I plug it in, I'm going to get negative 5. Negative 6 here is negative 3, so plus plus 5/3 is greater than or equal to 2. Is this true? Well, that would be false. It is less than So this part is false over here. So because of that, I know that my answers have to lie between -5 and that. If I use -5, hopefully we'll see that if I say -5 in here, this is going to be -5, -4 here. And -5 here is going to make this -2, which makes that 2. And is 2 greater than or equal to 2? Well, yes, it is. So it would be true on 5. But it did have an equal sign. So our answer to this one should say the following. It should be everything from -5 inclusive to -3 exclusive, because we cannot include -3 in this one. All right, let's take a look at the next one, example number 3. It's saying that x plus 5 over x plus 2. Before we do that, actually, I did want to do this because G asked me to do this. I don't normally do this, but if you have a calculator, let's take a look at your calculator. This is a good way to check your work. This is not meant for you to do this so that you can skip out on the work. That's not the important part here. So let's just look at it. Take your calculator. You're going to plug in to the y equals. You're going to do the first equation, x plus 1 over x plus 3. And then for the second one, you're going to say 2. And then go ahead and pause, plug that in, and then when you're done, come back and hit play and we'll get going. Okay, now I want to graph this. I'm graphing it. It's showing me this particular thing right here. Here's 2, and it's saying they want all the solutions that fall that are greater than 2. Well, if I'm looking at this equation right here, I see right here it's above the 2. 2 is this line right here. It's above the 2 right here, but only from the place where it crosses to the place right here. So from -5 to -3, that is where I'm going to find all of the parts of this graph that are greater than or equal to 2. That's basically how you would do this. But keep in mind, as I just said, there's no substitute for the actual math. If you decide to just do this and not the math, you're probably going to regret doing that. So I would tell you just to keep on working on this algebraically and check your work with your calculator. So this one, it's already set up. All you have to do is set things equal to 0 and solve. So we're going to set this one equal to 0. X plus 5 is equal to 0. So x is equal to -5. This one is x plus 2 is equal to 0. So this one is x equals -2. This one is your vertical asymptote. You're going to draw your line here. We have -5, -2, and 0. In terms of the picture itself, it's saying less than 0. So this is -2. It cannot be this. So we're just checking numbers on either sides of these things. So if I plug in 0 for both, 5 over 2 is less than. That is a false. If I check the next one, -5 to -2, so just -3. If I plug in -3 right here, I'm going to get 2. -3 in for this one is -1. That's going to be -2 is less than 0. That is true. And then if I do -6 in here, -6 will give me at the top a -1. At the bottom, -6 gives me -4. 1/4 is less than 0. That is false. So it's telling me my solutions are here. It can never be -2. -5, this one doesn't have an equal sign. So this is an open parenthesis, -5 to -2, open parenthesis. They go pretty quick once you get the hang of them. Let's look at this next one. This one is one of those where we could do that. Now, one of the things that I do to solve these sometimes is something a little bit different. Sometimes on these, one way to do this where you're not doing quite so much work maybe would be the following. I'm looking for those points that are boundary points. If I look at this, that vertical asymptote is going to be the vertical asymptote no matter what. So it's telling me that x minus 1 is equal to 0, x is equal to 1. That is the vertical asymptote in this problem. That's not going to change. Finding the other one means I've got to actually bring the 2 over, multiply top and bottom by x minus 1, combine the numerators. But you could also do it this way. I'm going to leave out the symbol and just say it this way. X over x minus 1 is equal to 2. Now, if I multiply the x minus 1 over to the other side, or multiply both sides by x minus 1, that means I'm going to end up with something that says this. And then I want to solve this, so I'm going to say 2x minus 2. I'm going to move the x to the right. I'm going to move the 2 to the left. And so it's saying that x is equal to 2. This will be your other solution right here. So if I look on a picture of this, that's kind of what I would see. I'm not real partial to having to graph a rational expression, so I don't usually do that. I just like to use the number lines. They're easier. So I'm just going to go down here below it, put this in. I've got two numbers. Here's 0, here's 1. And I know this is my vertical asymptote, so it can never be that one. And then 2, that one's going to be that one that I'm going to have to test against. So plugging in values, looking at 0. If I plug in 0 for this one, I'm going to end up with 0 being greater than 2. That is false, so this is false over here. And if I look at the other one, greater than 2, I'm just going to plug in a 3. If I plug in 3 at the top, I get 3. 3 at the bottom is 2. They're saying 1 and 1/2, or 1.5 is greater than 2. That is false. Now, the next one is kind of tricky because you've got to do a little bit of work here to actually get an answer. But we have to think about our picture. Our picture is going to do something like this, where we have this and we have this. Well, it's always going to go up or down. It's always got to do that, which is telling me that this area right here, more than likely, it's got to be true. One part of this has to be true. At some point, it has to be taller than 2. And since the other 2 parts were false, it stands to reason this one should be a true. If I were to do this math, putting it in just to check the answer, I would use 3 over 2. So if I put in 3 over 2, and 3/2 minus this leaves me with 1/2, and when I invert and multiply, I'm going to get 3, and 3 is greater than 2. This does check out. That means this part is going to be true right here. There are no equal signs in the vertical asymptote there, so the answer here is going to be 1 to 2. That is the interval that makes the most sense. 5. So 3x plus 5 is equal to 0, so that means x is going to be negative 5/3. And then this one says 6 minus 2x is equal to 0, so negative 2x is equal to negative 6. X would be positive 3. So, looking at my picture, I know that I've got 1 at negative 5/3. Here's 0. I've got 1 at positive 3. This is our vertical asymptote, so it can't be equal to that. I'll put that in here just so we're clear. There is that one. This one, we can use negative 5/3 because there's an equal sign here. Now I just need to test some values, figure out what I'm looking at here. If I'm looking at 5/3 in between those, I'll go to out here, negative 2. Testing negative 2, if I put negative 2 in here, I'm going to get negative 6 plus 5 is negative 1. Oh. And then, negative 1. And then at the bottom, if I put in negative 2, I'm going to get 10. So this is negative 1/10. It's supposed to be greater than or equal to 0. That is not true. So this area is false. When we get to here, I can test 0 because 0 is an indicator here. It's in between the two values that I found. So if I put in 0, 0 for the first one gives me a 5. 0 for the second one gives me a 6. That is true. So this part right here is true. And if I were to use a 4, positive 4, that's 12, that's 17. And 4 at the bottom is going to give us negative 2. And so it's a negative number. That can't be larger than 0. So this is false. We can include negative 5/3, but we can't include 3. That would be our solution to this interval. For the last question, I would like you to do that one, and then we will come back and take a look at it. I'll give you a few minutes. Pause the video. All right, here was the answer. Hopefully this is what you came up with. I put the graph on there as well so we could see where everything was less than, and it's only a very small amount where it could be. In this case, it was between 3 and 4 was false. It was above the line. So that is rationals in terms of inequalities and how to state your answers. Hopefully this makes sense to you, and we will see you in class very soon. Have a good one. Bye.